Welcome to G Fun Facts Online. Today, we are going to dismantle a 90-year-old dogma in the world of physics. For nearly a century, the scientific community operated under the assumption that the book on magnetism had only 2 chapters. We thought we had the full picture, but it turns out we were missing an entire dimension of magnetic reality. We are talking about the discovery of altermagnetism, a third fundamental state of magnetic matter that was hiding in plain sight. This is not just a minor footnote in a textbook. This is a revolution that rewrites the rules of quantum mechanics in solids and promises to change the way we build computers, memory, and sensors. To understand the magnitude of this discovery, we first need to look at the history we are leaving behind. Since ancient times, we have known about ferromagnetism. This is the force you are familiar with. It is what sticks a photo to your refrigerator. In a ferromagnet like iron, electron spins march in lockstep. They all point in the same direction, creating a strong, macroscopic magnetic field. This behavior breaks what physicists call time reversal symmetry. If you ran the film of the universe backward, the spins would flip, and the state would change. This energy difference between spin-up and spin-down electrons, known as spin splitting, is what makes ferromagnets so useful for spintronics, allowing us to filter and control electron spins. Then, in the 1930s, the physicist Louis Néel opened the second chapter. He described antiferromagnetism. This is a shy internal order where spins alternate in perfect opposition. For every electron pointing up, there is a neighbor pointing down. They cancel each other out perfectly, leaving the material outwardly magnetically dead. For decades, we believed this was the only dichotomy. You either had the parallel, strong field of a ferromagnet or the anti-parallel, zero field of an antiferromagnet. We built our civilization on this binary. We built hard drives on the first and read heads on the second. But we were wrong. Lurking in the blind spots of our symmetry classifications was a third option. In 2019, a team of theoretical physicists, including Libor Smejkal, Gyro Sinova, and Tomas Jungwirth, began noticing anomalies in the Hall effect of certain materials classified as antiferromagnets. They realized that our definitions of symmetry were too rigid. We had been assuming that the rotation of spins and the rotation of the crystal lattice were always coupled. By decoupling these using a framework called spin group symmetry, they found altermagnetism. So what exactly is an altermagnet? It sounds like science fiction because it combines properties that were previously thought to be mutually exclusive. Macroscopically, an altermagnet looks like an antiferromagnet. It has zero net magnetization. If you hold a compass up to it, the needle will not move. There are no stray fields. But microscopically, it behaves like a ferromagnet. It harbors massive, spin-split electronic bands. This means that inside the crystal, the electrons are strongly polarized by spin, even though the material itself has no external magnetic field. To visualize this, imagine a crystal lattice. In a conventional antiferromagnet, the atoms with spin-up and the atoms with spin-down are related by a simple translation or inversion. If you flip the spins and move to the next atom, you get the same picture. This symmetry forces the energy levels of the electrons to be identical or degenerate. An electron moving through the crystal feels no preference for spin-up or spin-down. But in an altermagnet, the relationship is different. The atoms with spin-up and spin-down are related by a rotation. Picture the spin-up sublattice looking like a pattern of dumbbells aligned horizontally. Now picture the spin-down sublattice located in the gaps, but identical and rotated by 90 degrees, like vertical dumbbells. Because of this rotation, an electron moving horizontally sees a different electrostatic environment than an electron moving vertically. This breaks the degeneracy. A spin-up electron might find it easy to move east-west, but hard to move north-south, while a spin-down electron experiences the exact opposite. This creates a spin splitting that is highly anisotropic. It does not look like a uniform shift. In momentum space, it looks like a cloverleaf or D-wave symmetry. This was the eureka moment. It meant we could have strong spin currents without the baggage of external magnetic fields. Once the theory was in place, the hunt for materials began. The physics community realized that altermagnets should not be rare. They should be hiding in materials we had already discovered, but simply misclassified. The fruit fly of this revolution became manganese telluride. For decades, manganese telluride was a textbook antiferromagnet. But when researchers looked closer at its crystal symmetry, specifically at the non-magnetic tellurium atoms, they realized they sat in a way that broke the symmetry between the manganese sublattices. In 2024, experimental confirmation arrived with the force of a thunderclap. Teams used angle-resolved photoemission spectroscopy, or ARPES, at the Swiss Light Source and DESY to map the energy levels of electrons in manganese telluride. To prove altermagnetism, they had to measure both spin and momentum simultaneously. They needed to see that electrons moving in one direction had spin-up, while electrons with the same energy moving in another direction had spin-down. And that is exactly what they found. They did not see the single degenerate line of an antiferromagnet. They saw the bands split apart, and the splitting was massive, up to 1.4 electron volts. This is a crucial detail. In traditional magnetism, coupling an electron spin to its motion usually relies on spin-orbit coupling, a relativistic effect that is generally very weak and requires heavy, rare elements like platinum. But the splitting in manganese telluride was far larger than anything relativistic effects could produce. This proved that the effect was coming from the electric crystal field itself. Because of the rotational symmetry breaking, the electric field pushes spin-up and spin-down electrons into different orbitals. This means altermagnetic effects are robust at room temperature and can be generated in cheap, light, abundant elements. We do not need rare earth metals anymore. The list of candidates is now exploding. We have ruthenium dioxide, a common conductor used in resistors, which was the first predicted altermagnet. We have chromium antimonide, a high-temperature candidate. We have complex metallic crystals, like multivalentmn5si3, and even 2D altermagnets, like ruthenium fluoride, that could be used in atomically thin devices. Proving this was a detective story in itself, because conventional probes are blind to altermagnetism. A standard magnetometer reads 0. Standard neutron diffraction just sees anti-parallel order. It required state-of-the-art synchrotrons and a new way of looking at X-ray magnetic circular dichroism to finally see the telltale fingerprints of this D-wave order. So why does this matter to you? Why is this a technological renaissance? Because altermagnetism solves the biggest bottlenecks in modern electronics. Let's talk about memory. Magnetic random access memory, or MRAM, is considered the holy grail of computing. It has the speed of RAM with the non-volatility of a hard drive. But current MRAM is limited because ferromagnetic bits interfere with each other. You cannot pack them too tightly, or their magnetic fields will corrupt the data. Altermagnetic MRAM solves this. Because they have zero net magnetization, bits can be packed atom to atom without talking to each other. There is no crosstalk. They are also immune to external magnetic fields. You could wipe a ferromagnetic hard drive with a strong magnet, but an altermagnetic drive wouldn't blink. Furthermore, altermagnets enable a new phenomenon called spin splitter torque. When you pass a current through an altermagnet, the electrons naturally polarize based on their flow direction relative to the crystal axes. This allows for field-free switching. You can write a magnetic bit simply by changing the direction of the current, without needing external magnetic fields or heavy metal interfaces. It is efficient, scalable, and inherently fast. And speaking of fast, let's talk about terahertz electronics. Ferromagnets are sluggish. Their dynamics are governed by precession in the gigahertz range, which is why your CPU speed has plateaued. Altermagnets behave like antiferromagnets dynamically. They snap back into place using exchange energy, which is massive. Their natural resonance frequency is in the terahertz range, 1,000 times faster than gigahertz. This opens the door to terahertz emitters and detectors, which are critical for 6G communication and beyond. This fills the famous terahertz gap between electronics and optics. The implications extend even further into neuromorphic computing. The brain does not process binary ones and zeros. It processes spikes and pulses in a massive interconnected web. Altermagnets are ideal for mimicking this. Researchers are designing spin neuromem chips, where altermagnetic tunnel junctions act as neurons and synapses. The analog nature of the spin splitting allows for weights in a neural network to be stored directly in the hardware. And because there is no magnetic crosstalk, these artificial neurons can be packed as tightly as biological ones. There is even potential in superconducting spintronics. Usually, magnetic fields destroy superconductivity. But altermagnets have no magnetic field. This allows us to couple superconductors with altermagnets to create Josephson junctions that could host Majorana zero modes. These are exotic quasi-particles that are their own antiparticles, and they are the building blocks of topological quantum computers, which would be immune to errors. We are currently standing at the shore of a vast, unexplored continent. The years 2024 and 2025 mark the landing, but the next decade will be the colonization. We are moving from discovery to design. Scientists are now using AI to find the perfect altermagnet, one that is a semiconductor for logic, operates at high temperatures for industrial use, and is made of non-toxic elements. We are also exploring strain tuning. Because altermagnetism depends on the precise rotation of the crystal lattice, it is incredibly sensitive to strain. Stretching or squeezing the material can turn the effect on or off, leading to the concept of piezo-altermagnetism, where mechanical vibrations drive magnetic computing. Altermagnetism has forced us to unify our understanding of topology, magnetism, and relativity in solids. For 100 years, we played with only two colors of magnetism. We built a civilization on them. Now we have discovered a third primary color. Altermagnetism combines the stability of the stone, the antiferromagnet, with the agility of the wind, the ferromagnet. It promises a world where memory never fades, computers think at the speed of light, and our devices are powered by the subtle, hidden symmetries of quantum geometry. The third state is unlocked, and the revolution has begun. Thank you for listening to G Fun Facts Online.